Live streaming is on.
Okay, so we are online. We can start, and we have a new day of our source code festival. Thanks for everybody to be connected, and this, as most of you know, is the first festival on source code organized by the University of Torino and Codexpo. And today we have a special event. It's really a honor for me and for all of us to have here with us Don Eyles. And I have to thank a lot also Dario Kubler, who is also with me moderating the session today from the Asimov Association. It's Associazione Italiana Modelli Fedeli. And I think that he will show us in a moment also what they do, because they do very incredible things. They built the Apollo guidance computer, this key, which is working. And so we have not only the author of the software, who will talk about everything, but also a replica which is working. And this is, I'm very happy that we can have him here today. Is one of the responsible for the software that was on board of the Apollo missions and was very important to bring man on the moon. And Don entered the Draper Laboratory in the MIT when he was very young, and he worked there to develop the codes that actually managed to land safely man on the moon. He will talk about his experience concerning the coding, the software, and everything. And it's really a great honor. And Don, it's your stage. So thank you very much for being here today.
Well, thank you very much for the invitation. It's a pleasure to be with you this morning. It's morning where I am in Boston, Massachusetts. I'm going to basically go through the various source codes that I encountered during 32 years of working on the space program under NASA contract. I was employed by MIT Instrumentation Lab, which became the Draper Laboratory. If you want to start my presentation and put it on the screen.
Can you see it?
No, I do not see it. Do you see it?
Myself, yes, but let me... I have a window. Let me see the following. Let me stop this and try again. Now, do you see your presentation?
I do see it now, yes.
And full screen, right?
Excellent.
Okay.
Excellent. So you see a list of the things I'm going to talk about. The very first, George, is in brackets because it's historical. I did not actually use the George language. Next slide, please. I'm going to start back in the early 1950s by talking about MIT's Whirlwind Computer. In a building that still exists on Massachusetts Avenue. It was a computer that was originally thought to provide a simulation function, a flight simulation function. It never achieved that, but it was a historical computer. It used vacuum tubes instead of transistors or chips. It was a very big day for that computer when it was finally able to achieve 7 hours of continuous operation. It pioneered various technologies, notably magnetic core memory, also multi-bit operation. The team was led by Jay Forrester, whose picture you see. Next slide. And that, I will not go through this, and it may not be very legible, but that is the instruction set for the Whirlwind computer, for the machine language of the Whirlwind computer. Next slide. Now, this man is going to pop up several times in this presentation. This is Hal Lanning, who I knew very well, especially in later years when we played tennis together. He had a hand in many of the notable events that took place at MIT connected to the space program. Immediately after Sputnik, he and some others started designing a Mars flyby mission. This was in 1958. And the specifications for that mission identified many, all except the crew interface of the systems that would be needed to go to the moon. Another contribution from Hal was the executive or operating system of the Apollo computer, which he conceptualized in the early 1960s. Next slide. But the thing I want to talk about now is George, which was a creation of Hal Lanning. He said it had to do with a radio show in which there was a detective named George Valentine, who would say, if it's a tough job, give it to me. But his motivation was that he was doing trajectory work using the Whirlwind computer and found it very awkward to use its machine language. It occurred to him that he could write a program which would translate a description of the equation that he wanted to program, would translate that from into machine code. In other words, it was a compiler. Next page. And this is what he said about it when he published about it in 1953. He said, nearly everyone who has had a problem to solve on a large-scale digital computing machine, and it's ironic that that machine by modern standards was tiny, but what he called a large-scale genuine digital computing machine has probably felt that it would be convenient if you could give the machine the problem in ordinary mathematical language. We have been motivated by sympathy for this feeling in writing the program for Whirlwind that will constitute, we hope, a useful step in the indicated direction. The effect of our program is to create a computer within a computer. I would suggest that a great deal of computer science that's happened since that time traces to this statement. Next slide. This was acknowledged to be the first compiler ever written. Grace Hopper in 1956 described it as the predecessor of several of the early compilers that are listed on the slide. And John Backus, who led the Fortran team and who received a demonstration of George in 1954, he acknowledged the primacy of Hal Lanning's achievement. Next slide. We've gotten to the year 1966, and I've graduated from college. I found a job at the MIT Instrumentation Lab. I was assigned to work with the man whose picture you see, Alan Klump, and it was a joke in those days to say, "How do you land on the moon?" Klump. And the first assignment he gave me was to use the Mac language. And the Mac language was an evolved version, a highly evolved version of Hal Lanning's original George. The Mac stands for MIT Algebraic Compiler, although some people will give you a different reading of the acronym. Next page. And I wanted to show you a few examples of Mac code. Its innovation, the unique thing about Mac was that it allowed a 3-line format for writing code. There was the main line, which was designated by an M in column 1, but you could also have exponent and subscript lines. And you can see that in these examples, which I've quoted from a paper by Dick Batten. Another way in which the exponent line was used was to mark, this is in compiler listings, was to mark the type of data. You can see in that bottom equation the dashes, the underlines that are above the two vectors, well, several vectors, and the asterisk that's above the M Those indicate that the ones with the line indicate that those are vectors, and the ones with the star that it was a matrix. Next page. The next page, please. And I go back when. Yes, these are some other examples of Mac code, and I included this slide to show you the coding forms that we were provided for writing Mac code. I did not use the coding forms very much, and I'm not sure anyone else did, but that's what they look like. Next page. And if you were wondering how we actually input the code, this is how. This is an IBM key bunch machine. The fact that there were exponent and subscript lines meant that the exponent and subscript were on different cards than the main line, and so you had to get them in the right position, which was not necessarily so easy. So in that sense, Mac was not such an easy language to use. My assignment, which I was given by Alan Klump, was to fix or improve the statements that were printed out by a program of his that he named after his wife, Susan Kay. On the next slide. And my job was to improve the printing that was done using the Mac language. Next slide. For some reason, when you switch to the next slide, go back one. For some reason, it doesn't come up immediately. We're now going to talk about the Apollo computer and the code for the Apollo computer. And you've probably seen this picture before because I've used it in other presentations. But that's the computer shown from two angles. And you can also see in the right-hand view the modules that contain the code in read-only memory, of which there was 36K of 15-bit words. They were actually 16-bit words with 1 bit reserved for error checking. Next slide. Is the next slide up for you? I don't see it yet.
Yeah.
There it is.
Mm-hmm.
We don't have to spend much time on this because it doesn't have to do with code. And now I'm seeing the slide with the book on the wooden table. Is that correct?
Is that correct? Yes.
Okay. We did not, if you're picturing terminals of any kind on our desk, you've got it wrong, because these were pre-terminal days. And if we wanted to think about the code, what we looked at was paper. And what you're looking at is a full listing of an Apollo program. That happens to be the Apollo 13 LIM program. You can also see to the right, in fact, go to the next slide. That's a coding form for Apollo computer code for the onboard computer. Next slide. And there were, in fact, 2 languages that we could use to code the AGC. The memo on the left, Hugh Blair-Smith's memo 9, is the guide for the assembler language that we call BASIC. There was also an interpretive language. I'll be showing you this momentarily, and that's the manual for that. Next slide. And now there are going to be 3 pages of code, and I'm not going to go through it in detail, but I wanted to show you what it looked like on the page. And the page you have up now is good. You see the columns of numbers to the left. The first number is the memory address of that line of code. The second column is the content of that word in octal. Now, the octal number system was a great advantage to us in coding the AGC, because one octal digit, one base 8 digit, translates directly into 3 binary digits. So it became a very handy way to express the binary data in a way that allows you to visualize the actual bit pattern very, very easily. Of course, into those 15 bits that are portrayed there had to be packed, in the case of the basic language that's at the top of the page, had to be packed both the op code, the operation code, and the address. About a third of the way down the page, however, the code changes from the basic language to the interpretive language. Now, this was also managed by the Yule assembler, the assembler that created by Hugh Smith, that assembled this code. But now, instead of actually writing the machine level instructions, what the interpreter inserted, starting with the line just below the TC interpret. The TC interpret is the last machine language instruction that is passing control to the interpreter. The interpreter then reads the code in the successive lines and knows how to interpret them. On those lines, in general, operations were packed 2 per line, and the addresses to which those operations pertained were then listed in the next words. So you see at the very beginning a vector times scalar operation, and then a push down into the push down list, which was part of the interpretive code. Thank you for indicating that with the cursor. By handling the code in this way, a full address could be given. It was independent of the bank structure of the memory. Go to the next slide. You see the exit in about the middle of that page. You see the exit instruction. That's leaving the interpreter and going back to the basic language. Next page. Now, I mentioned the bank structure of the memory, and this shows how this shows how we were able to address the full 36K words of memory, even though we only had 15-bit words that had to include the memory address and the op code. And the way that worked was that both the read-only memory, which we called fixed memory, and the random access memory, which we called erasable memory, both of those were packaged in banks, what were called banks. And for each type of memory, some of those banks were permanently accessible. You see at the very top to the right, the first 5 banks of erasable memory are available all the time. However, there are 5 additional banks, which, 3 additional banks, which were switched, meaning that a separate register indicated which bank was needed. So at any time you saw 5 banks that were always there, plus 1 more, which was chosen from among the others. And similarly with the fixed memory, the read-only memory, there were 2 banks of what we call fixed. They were always present, very valuable memory. But all the other code was in one of 30 banks that depended on those extra bits for the code to reference it properly. Now, next slide. The bank switching, of course, was awkward, but the awkwardness could be gotten around by the proper assignment, by thoughtfully assigning both the code to fix banks. In other words, code that was needed in a given part of the mission. If that could be assigned to certain banks, then bank switching would be relatively rare, wouldn't be needed too much. Now, this is an important illustration from Hugh Blair-Smith's Memo 9 that basically shows how an instruction repertory of 30-something instructions were provided, even though we only had either 3 bits or 5 bits available for the opcode. Instructions, for example, clear and add, which is the 4th one over on the top section. Clear and add is essentially fetch. That needs to be addressed both, needs to be able to address both the ROM memory and the RAM memory. And so only 3 bits in those instructions were devoted to the opcode, the clear and add code. And the other 12 were allocated to address. And as shown on the previous slide, those 12 bits were determined by which memory those addressed was determined by the bank register. Now, certain other instructions, such as the L exchange, the increment, the ADS, by definition, could only access random access memory that could be written, what we call erasable memory. And so in those cases, fewer bits were needed for the address, and they're making 5 bits available for the opcode. The second, the lower part of this diagram describes some other instructions that had to be preceded by an instruction called extend, which again added what effectively was an extra bit to the address. So by those subterfuges, an instruction set of something like 30, I would have to count them again, but 30-something instructions were provided. Next page. Here you can see, I'm going to show you a couple of code examples now that had significance to the missions. I'm sure you recall that on Apollo 11, or have read about the alarm problem on Apollo 11, which was caused by a problem in the hardware that flooded the computer with counting pulses relating to the rendezvous radar antenna. Now, the rendezvous radar, of course, was not needed during the lunar descent, but this problem did not depend on the radar being in use or even being owned. It had to do with an eccentricity, you could call it a sneak circuit, that caused, when the cockpit switches were in the wrong position, caused meaningless pulses to flood the computer. The solution for that, and this is code that we put in right after Apollo 11. It was code that was in the load, it was the program from Apollo 12 on. You can see from the comment on the right that what it does is it senses whether or not the switch for the rendezvous radar is in the position that could cause trouble. And if in fact it is, it sends a signal to 0, the rendezvous radar CDU. CDU meant control data unit. It's essentially a analog to digital converter. By sending that 0, we could prevent the flood of pulses if in fact the switches were set wrong. This is some code that was provided by Hugh Blair-Smith. I added the comment. Next slide. Another thing that happened in flight on Apollo 14 was the fact that the abort switch in the LEM cockpit was sending a erroneous signal to the computer that could have caused an abort, an involuntary abort during the lunar landing. And I was called as the one who wrote the logic that reacted to the abort switch. It was my job to figure out a way of defeating my own logic, so that this random signal from the switch, which was caused by some metallic contamination floating around inside it, so that it didn't ruin the lunar landing. So I'm going to show you the code that had to be defeated and talk a little bit about how that was done. Next slide. This is a contemporaneous flowchart of the logic that looks at the abort switches and initiates the abort programs if it sees them. Its official name was R11. For some reason, I dubbed it Rosencrantz. There was another monitor that I called Guildenstern, from the characters in Shakespeare's Hamlet, of course. Next page. And this is the code that implements that logic that was shown on the flowchart. There was a switch. You can see the very first paragraph of code there. Clear and add the flag word, which is a word in which various bits with different meanings were packed. Then masked with the let abort bit. In other words, all bits then became 0 except the let abort bit, and it would be 0 or 1 depending on whether that bit was set. So we've now isolated the bit in question. I mentioned the BZF instruction was an extend instruction that required the previous instruction to be extend. But that instruction meant branch on 0 to fixed memory. That would, if the let abort bit was still 0, that would skip around this monitor. So if you looked at this and said, how do I defeat this monitor? You might say, okay, I'll reset. I'll set to 0 the let abort bit. The problem with that was that at the moment we lit the engine for the lunar descent, the let abort bit would be set automatically. I should say at the moment we throttled it up, the let abort bit would be set automatically. And there was nothing we could do about that until it happened. So there would inevitably be a period following ignition when this monitor would be active. And of course, at ignition, you might anticipate that there would be some vibration and that the contamination in the switch might move around. So a solution that waited until the abort monitor was active and then turned it off was not satisfactory, because it left a dangerous period when the abort could still have occurred, and it probably would have been impossible to recycle and try again on the next loop around the moon. So that wouldn't work. You see that the next set of instructions is examining the Mod Reg or mode register, which was a place where, mostly for display purposes, the current program in process was indicated. We're looking to see if we're already in the deepest level of abort, which would be P71. So we're adding decimal 71 to the mode register, and then branching on 0, which would occur if we were in 71. We branch around any further checks. So, in fact, the solution to the problem on Apollo 14 was briefly to set the mode register to a wrong number. That caused the display on the disk key to look wrong, but it had very little effect on the actual flow of the code that was mostly being controlled by the ignition routine that was called Burn Baby, that was a set of code that I wrote jointly with Peter Adler after we realized that the procedures leading up to an engine burn were very similar to all different burns, meaning the descent burn, which we're talking about now, but also the on orbit and mid-course engine firings that were conducted by the programs called the P-40s. And that was running the ship, so to speak, so that setting the mode register to the wrong value did not prevent the engine from being lit and prevent most of the things that needed to be done automatically. I could go through the rest of this, but that was the significant part in terms of how we dealt with the problem on Apollo 14. Next slide. Now, there was actually a third language that you might not call a computer language. It was a human interface language, which was also important during Apollo, and that was the language that was used by the the display and keyboard, which you see in this illustration. This is the situation in the LEM cockpit during the visibility phase, P64. Next slide. And here's an enlargement of the DSKY. You see in the numeric display on the right, you see a verb and a noun, which are 0, 6, and 63. And you also see verb and noun buttons on the keyboard that's below. What this display is indicating, and this is the display that was present during most of P63, the verb 6 displayed noun 63 indicates a set of data that populates the 3 5-digit registers that are part of that numeric display. That very first number, 3036.3, you had to know implicitly where the decimal point was. That's the total velocity of the LEM. The next number, 92.7, minus 92.7 in feet per second. Feet per second is the altitude rate. And the 40,000 number is the altitude in feet at that moment. Next slide. Here's the display that was called up by Buzz Aldrin to find out what the problem was when we had the first alarm. The previous slide was a display, a noun and a verb initiated by the software. In this case, it was a noun and verb entered by the astronaut. Next slide. And with that preparation, I thought I would show you briefly the full procedure that was developed for Apollo 14. You see there are 4 strings of keystrokes. The very first string, the verb 21, noun 1, that enters the value 1010. At memory address 1010, it enters the value 107. 107 in octal is equivalent to 71 in decimal. By the way, the nerd joke at the time was Halloween equals Christmas, because oct 31 equals dec 25. There are 3, after that, there are 3 further strings of keystroke that set the various bits that needed to be reset. Once we'd passed the dangerous ignition point, we were then able to explicitly stop the aborts monitor by resetting, by zeroing the let abort bit. And once we did that, we could put the correct value of 63 in that very last set of keystrokes. We could put the correct value of 63 back in the mode register. And finally, at this point, we were back under normal operation. Next slide. So that was Apollo. Those are the various languages that were in use on Apollo. at around the same time as Apollo 11, a group of people who were Hal Lanning proteges, you might say, Dan Likely, Jim Miller, John Miller, they went and founded a company called Intermetrics. And the first job they undertook was to design a language for use in the space shuttle computers. And that language was called Hal S. Now, if you look up Hal S, in certain places, you'll see it called High Order Assembly Language for the shuttle. We all knew the real origin of the name, which was, in reverence, if you will, to Hal Lanning. And next slide, please. This shows an example of Hal S code. And you see that the same exponent, main, and subscript format that was created by the Mac language, which was an evolved version of Hal Lanning's George, is adopted here. Another innovation with the Hal S is that it could do character string operations. And you see in some of those lines of code a sort of apostrophe or comma over certain variables. That indicates that they are character string variables. So again, that was a technique created in the Mac language that was carried over into Hal S. Next slide. But the other thing that Hal S added was it was a language designed for real-time operation in the space shuttle's computers. So it needed the ability to do operating system type things such as schedule processes based on time and based on priority. And this is an example from the HAL user's guide. And the significant thing here is the schedule statements that are down towards the bottom. Those are very simple schedule statements because they only have a priority. But those statements can also specify that something was to be scheduled for operation at some time in the future or at some repeating frequency. So, in effect, the Hal S language combined the real-time features that Hal Lanning had conceptualized for the AGC with the Mac language, which was an evolved version of the original Hal Lanning compiler. So it's no wonder they named the language after Hal Lanning. We used this language in the shuttle period at MIT to build a number of simulations. One of them was called the OFS, or On Orbit Flight Simulation. And we used those. We were no longer in charge of writing the onboard code, but we used those simulations to verify various things that NASA was planning to do with the shuttle system. And while I was doing this simulation work, I realized that we needed a what you might call a paper pilot. We needed the ability, based not just on time, but also based on various conditions. We needed the ability to put inputs into the simulation. And so I wrote the first version of the timeliner language and the system to support that, which was a high-level sequencing language that sat on top of the hard-coded language. Now, I mention that now because I used Hal S in the first version of that, and it was the biggest coding job in Hal S I ever did. And the example on the previous slide actually came from a listing of the Timeliner compiler. Next slide. I didn't have an Ada manual to use, so I thought I would use a picture of Ada Lovelace, after whom the Ada language is named. I came to use this language in the mid 80s or late 80s. We became involved with the space station effort. And once more, we put together a simulation which was coded in the Ada language. to be able to, in advance of the real implementation, simulation that allowed us to identify problems and point the way ahead. And that was done in Ada. And at that point, I started creating a version of the timeliner sequencing system using the Ada language. Go to the next slide. As everyone here probably knows, the value, or one of the values of Ada, is the ability to do strict typing. In other words, to create specific data types and to specify how they can be used such that once you've successfully compiled, you have a much higher likelihood that nothing will be wrong. This shows the declaration for some of the types and the renames, as they were called, that specify what the result is if things of that data type are combined in certain ways. If comp pointer type, it stands for component pointer type, if those are added using the plus sign, the result will be another of comp pointer type. If they are compared using logical operators such as equal or not equals, greater than, less than, then the result will always be a Boolean. And there are hundreds of these statements of this kind in the Ada version of Timeliner. Next slide. And here, in fact, is some Ada code deep in the nesting of the parser. But this is the code where the whenever statement, one of the real-time statements in the Timeliner language, where it is being parsed. Next slide. Now, as I say, and I'm nearing the end here, as I said, the Timeliner language was originally created as a simulation driver. But in about 1990, we realized that NASA was talking about a language called UIL, for user interface language, for use on space station. And we realized that many of the characteristics they were interested in were already present in Timeliner. And we had the fairly mature Ada version of Timeliner at that point as part of the simulation. We were able, over the course of really 2 years, to get the operation community at NASA, both the payload folks and the core operation people in Houston, to get them on board with Timeliner being the best solution for their problem. And in fact, in 1992, it was selected to play that role aboard the space station. So all the other languages were languages I used. Timeliner is a language I created and also used, but never used to the extent that it's in use now aboard space station in 3 versions. Go to the next slide, please. Timeliner is both a language built around temporal constructs such as when and whenever. It supports logically parallel processing by running what's called sequences in parallel. And it was designed to be programmed by operational experts. In other words, not to be a difficult language. But Timeliner also means the system for creating and validating scripts on the ground, executing them on the target system, for example, the spacecraft, although, of course, this can be applied to other systems. And if needed, monitoring and interacting with the execution of these scripts in real time. As I say, Timeliner is in heavy use aboard the International Space Station now in 3 versions, in Japanese experiment module and in the core and payloads part of the NASA modules. Timeliner is structured for adaptability to other applications, and it enables an evolvable, flexible software architecture in the sense that the sequencing, the turning of things on and off and telling them what to do can be incorporated into Timeliner scripts and decoupled in that way from the actual hard code written in that's part of the permanent software system of whatever system or spacecraft we're talking about. Next slide. This just shows the data flow through the compiler, which is on the ground and on board the spacecraft. You see the compiler gets the raw script from the programmer. It has access to a database that includes everything needed to describe the onboard system. It outputs what's called a bundle file. A package of timeline sequences is called a bundle. Those go to the executor on the spacecraft, and also outputs, of course, a listing file. The listing file, by the way, also goes to the spacecraft to support displays that allow the execution of these sequencing scripts to be monitored in real time. And that's shown in the executor with the input of the bundle file and access to the data on board is able to do the sequencing, to send the commands and insert the data as necessary. Next page. And here's an example of a very simple sort of elementary timeline or script that actually monitors 4 different pieces of data from the system and acts accordingly. That first sequence called arrow mode and sets one or the other value to arrow mode depending on which of 2 events happens first. If altitude is under 400,000 before event 301, then that mode is set to 1. If they happen in the other order, it's set to 0. The next sequence is a thermostat. It includes one of the powerful features of the timeliner language is the define statement, which allows a condition such as temperature greater than 80. It could be much more involved than that. It could be temperature greater than 80, and this condition or that condition, in other words, anything that can be coded. And once that define statement is in place, that condition can then be referred to by that name that was created. In other words, too hot. So the next statement, the whenever statement, is saying that whenever it's too hot and the heater status is on, call heater off. Heater off is a subsequence, basically a subroutine that in this case sends the command to turn off the lab heater. The format of the commands is implementation dependent. Next slide. Well, I forgot that I left that picture in there, but that's me wearing a Timeliner t-shirt. I took that picture of myself last night, and I think we've come to an end. You can go to the next slide. These topics I've been discussing are discussed in much greater length and probably more coherence in my book, Submersed in Luminary. And that's the end of my talk. I hope we still have time for questions.
Thank you very much, and for this very interesting and fascinating talk. Let me just do this. So yes, we have some time for questions. Maybe, I don't know if Dario has already some question to Don, so he can check the chat and see if I can get some question from the audience. Otherwise, I have some questions myself. Dario, maybe you have the muted microphone.
Yeah, no, I was just showing also the book that Don signed for me when he was last time. It was in Italy 2 years ago.
Yeah, and we hope we can invite him again soon after.
So maybe I can just ask my question to Don.
Yeah.
Very shortly. How big was the difference between the software routines on board the lunar module and the one on board of the common module, the AGCs versus the LGCs?
Everything that you would call operating system, was the same. The routines for communicating through the DSKY were the same, but the selection of nouns and verbs, of course, would be different on the two computers. And similarly, all the code that had to do with the mission, meaning things like the lunar landing, the on-orbit maneuvers, and so forth, those were different for the two computers. So it's probably fair to say that about half, maybe a little less than half of the code between the command module and the LIM were in common, and the rest was different.
Great, thank you, Don. And I assume that the frequency of the clock were the same. I mean, the hardware were basically the same, and the memory size was also the same, right?
That's correct. That's correct. The clock was a centisecond clock. We were timing in hundredths of a second in terms of our timing inside the AGC.
Yeah. Okay, and this is interesting to know because if everybody remembered movie Apollo 13, at some point they said, "Oh, fortunately, we have two identical computers, one on board of the common module, the other on the lunar module. So it's easy. We just transfer the software from one computer to the other one, and we let the computer on the lunar module to drive the mission." In reality, what they did was just putting the state vector, copying from one module to the lunar module. But then we know that there were not all the software functions running on the lunar modules. And that was the main difference, right?
But the things, yes, but the functions that were needed were already in the lunar module's code. It would have been, it wouldn't have worked. It wouldn't have begun to work to remove the memory modules from the computer and the command module and insert them in the computer and the LIM, because the interfaces, the hardware interfaces of the LIM computer and those of the command module computer were different. And it just would not have worked at all. But everything that was needed was in the LIM computer, the ability to set up a burn, to do an engine firing with the lunar module's engine, as was done to correct the course as the spacecraft, the joint spacecraft, looped around the moon and headed back to Earth. They have the lunar module pushing the entire heavy stack, meaning the LIM, the command module, and the service module. That had been tested briefly on, I believe, Apollo 9. And so there was some small experience in controlling the whole stack from the LIM. But of course, the detailed procedures for doing this on Apollo 13 needed to be worked out. And the effort that took place on the ground in Houston to create checklists, create procedures for the rest of that mission following the explosion, that was indeed an epic struggle, an epic effort. We were doing our best to support that in Cambridge, but personally, I had very little role in that because I was a lunar landing expert, and of course we could not do a landing, and my expertise was not really that relevant. So I was bringing people coffee and running down to the computer room to pick up output and so forth during the Apollo 13 crisis.
Yeah, Don, we have a question from Gian Maria, and I forgot to tell to the audience that you can put the questions in the chat and I will read them to Don. So the question from Gian Maria is the following. Timeliner lets bundles run in parallel, but does it take concurrency into account, or are programmers required to plan ahead to avoid concurrency problems such as data races?
It takes them into account, if I'm understanding the question properly. Multiple bundles can be installed in the executor at the same time, and within each bundle, there can be multiple sequences and subsequences, and the memory for all of those is kept separate. And I'm sure you could design timeliner scripts that would interfere with each other, but everything is there to allow you to avoid that.
Yeah, thanks. So I have a question myself. So each Apollo mission had the same code loaded, or were there differences depending on the mission?
There were differences as the software evolved. In other words, as new capability was added. The last three landing missions, Apollo 15, 16, and 17, did use exactly the same code. But for every mission before that, there were changes in between missions. For example, after Apollo 11, we made two important changes. One of them I've already described, the little bit of code to guard against the eventuality that caused the alarms on 11. But the other thing that we added was a new noun. Remember the verb noun language that I talked about? We added a new noun that allowed the spacecraft's position to be updated the very last minute based on tracking data that was gathered when the LEM came around the moon for the last time before the landing. And by doing that and having that noun that allowed that data to be put in, Apollo 12 was able to land right where it wanted to be, as opposed to Apollo 11 that landed about 4 miles downrange of where it was targeted to land. Of course, that didn't matter. As Armstrong said to me once, anywhere I can land on the moon will be interesting. But every mission had to do more than the last one. And the goal assigned to Pete Conrad on 12 was to land within walking distance of a surveyor spacecraft, unmanned spacecraft that had landed on the moon several years before. And he was able to do that. And every mission after that was able to land accurately. The key thing was that at the beginning of the visibility phase, when the LEM's attitude changed such that the lunar surface ahead was visible in the cockpit, at that moment, would we be close enough to where we wanted to be that the astronaut looking out the window would recognize the pattern of craters that would show him where the spot he wanted to go was. And in fact, that was achieved on every landing after 11.
So let me check other questions. So another question is, how did you test your lines of codes? Because you showed that was actually long, complex. So how was that going?
Oh, do you have another hour or two?
Yeah, well, okay.
There were a number of simulations. Simulation was, we spent a great deal of our time, maybe most of our time, doing simulations, and those existed in a number of different flavors. Each type of simulation had its strengths and its weaknesses, and by putting all of those together, we and the community at large, meaning NASA, Grumman, and other actors, were able to, I think, create very reliable code. In-house at MIT, we had the ability to run short segments of code and look at trace, where we saw what every instruction was doing. We also had a all digital simulation that ran in the mainframe, very slowly, by the way, that that combined the onboard software with surrounded it, shall we say, with code that simulated the equations of motion, the environment, so that when certain outputs were put out by the software, the appropriate inputs would come back from the simulator. And in the early days, when our mainframes were Honeywell 1800s, it would take about 4 hours to run a complete lunar landing of about 20 minutes of time. But that gave you exact, repeatable results. Meaning, if something went wrong or if something happened that you didn't understand, you could run again with additional output enabled so that we would get more information out of it, and we would be guaranteed the same problem would occur again. The other simulator that we had at MIT was what we call the hybrid. It was called that because it combined digital computers, meaning the AGC, another digital computer that did I/O, with analog computers, and the actual how shall I say it? The actual guidance equations, if you will, the actual equations of motion, the environment was provided by these analog computers. And because analog computers at that time do this way faster than a digital computer could, our hybrid simulation was able to keep up with real time. That was the simulation we used when we validated the Apollo 14 fix, the Apollo 14 procedure that I showed you earlier. And in fact, the first time we ran it, we crashed because I had overlooked something. But we got it working, and using the hybrid simulation. The hybrid, we would get the output in real time on strip charts, where the old-fashioned polygraph, where a roll of paper comes out with a spiggly needle. Of course, with the hybrid, you could not depend on reproducing a problem, because there were enough subtle factors in how the human inputs were that prevented having a bit-by-bit repeatability. Outside of MIT, Grumman had a simulator. NASA had very good simulators, especially for the visual displays. And all of those simulators contributed to it.
That's interesting. Wow.
So just a clarification. Don, was the hybrid simulator based in Boston?
Yes, okay.
In
Cambridge.
Yeah, in Cambridge.
Yep.
While the full simulator system was in the Cape, right?
Well, when you say full,
I mean,
yeah,
where you can get into the lunar module simulator and see the vision of the lunar landing site projected.
Yes, that was NASA had that simulator at Cape Canaveral and also in Houston. I used the one in Cape Canaveral quite a bit during the later stages. I flew many lunar landings, either with an astronaut or by myself, in that simulator called the LMS, which stood for Limb Mission Simulator. However, we did have a cockpit in Cambridge, and were able to use that cockpit when we needed to put human inputs into a simulation. We attempted to have a visual display, but it was unsuccessful and it was not useful.
Yeah, so that was done without the visual displays at the time.
That's right.
Yeah, so everything.
Dario, you've seen my other pitch a number of times, and I did include pictures of our hybrid simulation in Cambridge, but also of the LMS at the Cape.
Dario, do you have other questions?
Not from my side.
I have a curiosity, actually. When you show the Mac language, you showed us that you had actually 3 lines and also afterwards the following language with the same structure. And what was the advantage of having these written in 3 lines compared to, because I never saw, actually, it's for the first time that I see a language that allows to do that. So really write exponent, pedicles, and I mean,
It appealed to the mathematicians.
okay. But was it difficult to code it, or it was?
Yeah, yes and no. I mean, if you have to do it on one line, then one language wants the subscript in parentheses, one language wants them in brackets, etc. There are issues like that. So that was avoided, and it was more readable in a compiler listing. But it was a little harder when you were punching cards to get it right. So I would say there were advantages in both directions.
Ah, okay. Interesting. I never saw that, actually. That was something new to me. And
of course, subscript lines could have subscript lines. I think in some of the examples I put in the pitch, there were 2 S lines.
So it was possible to stack them out.
It was possible to stack them. I believe there were, I couldn't find an instance, but I believe there were cases where they were stacked 3 or 4 deep.
Okay, wow, great. And okay, and let me see if I have something else here. So one other question is about timeliners. So you mentioned that timeliner is actually used today for the International Space Station. Was that used also for the shuttle program and other programs?
Not on board the spacecraft. It was used on the ground at MIT, or I should say at Draper, because by then we had become Draper. It was used by us for simulation purposes on the shuttle project, but it was not used on board the spacecraft.
Okay, but then was used, and it's still used now on the International Space Station.
Yes, it is.
Yeah, great. So we don't want to exploit much of your time. It's already 6:30. So unless Dario has other urgent questions,
No, not from my side.
I can, yeah, so I can thank you really very much. It was really fascinating what you told us. And I'm very happy that you accepted our invitation to deliver this talk on this very exciting topic to our festival.
I've enjoyed it. I appreciate the invitation. I'm sorry we had the technical difficulty.
But this can happen, no problem with that. And we hope that we can invite you to come to Torino and Milano soon after this COVID we finish. So Don, thank you very much.
I would love to do that.
Great. We will keep in touch. So thank you very much for all your availability and kindness, and have a nice day for you. We are approaching night.
Yes.
Little by little, we're close to dinner, and maybe you are close to lunch. So thank you very much, and hopefully see you soon.
Well, thank you.
Thank you very much. Bye-bye.